Hello everyone, welcome again to High Pretty Accounts channel. And our subject today is performance management, and our topic is learning curve theory. Okay, what is learning curve theory? Actually, when you have labor and they're involved in making a particular thing that is a bit complex and some other conditions that we'll see later, actually, initially it will take much longer to produce the product, but as time goes, labor gets accustomed to how to produce the product and time actually gets lowered. So we are trying to learn the curve, the path taken until this point is achieved, right? Yeah. All right, so learning curve theory simply applies to situations where the workforce as a whole improves in efficiency with experience. So workforce becomes more efficient as time goes on. All right, the effect describes the speeding up of a job with repeated performance. So repeating it actually makes labor much more comfortable and actually much less time is taken to accomplish exactly the same job. So there is a theory that we will base upon. Actually, you have two theories. We have the Wright's model and also have the Crawford's model. Okay, I'll take a look at the model that is very common and actually will deal with just a single model, right? So actually, it will be based on Wright's model, although there is also Crawford's model. So our main focus will be on the Wright's model. So what does the Wright's model require? It states that, now remember, we are trying to take a look at the relationship between the units produced and the average, cumulative average time taken to accomplish one product, right? So that's why we are saying that cumulative average time, this is our first variable, right? Cumulative average time a worker takes to complete a job falls by a constant proportion. So that time falls. But with experience, the time would actually fall, right, by a constant proportion, maybe by a particular percent, let's say 20%, let's say 40%, whatever proportion, right? Just know that it's a constant. When now? After what? That the time fall by a constant proportion. Whenever cumulative units of output double. So whenever we have the cumulative outputs and then they double, we say that time has decreased by a particular proportion, right? Let's say that the first unit takes 10 hours. If units double, first unit, if they double, you have 2 units. So average of producing 2 units would be, let's say maybe units decrease by 20%. So the remaining time, the average time should be 10 hours times 0.8, right? Which would be 8. So that's how we'll proceed. Actually, don't worry about this. We'll see the computations down here, right? Okay, as for Crawford model, it is usually the opposite, but actually our focus here won't be on the Crawford's model. It is very different to the Wright's model. So let's focus on the method commonly used in exams, which is a Wright's model. All right, so as right here, back to Wright's model. For example, now let me give you that example. We say that cumulative average time to produce a product flows by a constant proportion when units of output double. So instead, we produce 1 unit and now they have doubled. So the double of 1 is 2, the double of 2 units is 4, the double of 4 units is 8, the double of 8 is 16, etc., etc. All right. So I'm just trying to conceptualize the actually I'm just trying to conceptualize the model so that we arrive at a particular equation, right? So beware of the number of jumps between the cumulative units. What do I mean by the number of jumps? For example, let's say you produce 1 unit and then you produce 16 units. How can you relate between 1 unit and 16 units? If 1 unit doubles to 2, this is the first jump. 2 doubles to 4, second jump. 4 doubles to 8, third jump. And 8 doubles to 16, which is the fourth jump. So we'll take a look on how the jumps can be actually related so as to come up with a particular equation, right? Okay, so 1 to 2 means 1 jump, right? So I could say that cumulative average time to produce 2 units should be equal to cumulative average time to produce 1 unit times something called learning rate. Now, you will come and learn this rate, right? We have something called learning rate. Learning rate could be, let's say, I told you that when units double, the cumulative average time falls by a particular proportion. So in case, let's say, whenever units double, time falls by 30%, we remain with 70%, right? Now, that 70% is what we call learning rate. If when units double, maybe they fall by the proportion that average time falls is 20%. To know the learning rate, you take 100% minus the 20%, and you remain with 80%. So that's how we determine the learning rate. Okay, so 1 to 4 means 1 would double to 2 and then 2 double to 4. So we'll have 2 jumps. So you see this number of jumps, these 2 jumps. So I would say cumulative average time for 4 units, which is here, right, should be equal to cumulative average time for 1 unit, which you obviously see here, times learning rate power how much? Now, learning rate, you see here now we have power 2 because there are 2 jumps from 1 to 4. 1 to 2 and then 2 to 4. Here we just used 1 jump, so this one was reflected here under this learning rate, power 1. And then 1 to 8 means that 1 to 2 first jump, 2 to 4 second jump, and 4 to 8 third jump. So cumulative average time for 8 units would just be determined as follows. I would say cumulative average time for the first unit here, as you see it, and we multiply by learning rate power 3 because 1 to 8 involve 3 jumps. Now let me ask one thing. What if you say 2 to 8? 2 to 8, I would say 2 jumps to 4 and 4 jumps to 8. So there are only 2 jumps between 2 to 8. So I could have said cumulative average time for 8 units should be equal to cumulative average time for 2 units times learning rate power 2 instead of learning rate power 3. So we do the same to 1 to 16. Would have 4 jumps, just like you see here, right? So simply speaking, CAT means cumulative average time. That means if you need to know the cumulative average time for first 4 units, I will take time for first unit, for second unit, for third unit, for fourth unit. I add them together and then I divide by 4. So beware of the weighted average. You can have cumulative total time, but also cumulative average time. All right. So that's what I just needed to show you here. Okay, you can proceed here and we say the learning rate and the learning effect. Actually, you need to know, someone can ask you for a learning rate of 50% and maybe a learning rate of 70%, which learning rate is better? Actually, by which learning rate labor learns more quickly? If you do not take a look at the equation, at the formula, you would say that the higher learning rate means that labor learns more quickly, but it is the exact opposite. The lower the learning rate, the faster labor learns quickly. And we'll see that in an exam, right? Okay, so where a learning curve applies, there is a learning rate and obviously a learning effect. All right. So as I told you before, the learning rate is usually expressed as a percentage, let's say 80% or let's say 70%. This is how we express our dear learning rate. So the learning effect is that. What is the learning effect? As labor takes much more time, the cumulative average time to make a product actually falls, right? And so we say as the workforce learns from experience how to make the new product, there is a reduction in time taken to make additional units. Simply like that, right? Okay, so we have to note the below things before going to an example now. Okay, so when units of output double, cumulative average time falls by. So to know exactly that proportion or fraction or percentage by which the cumulative average time falls by when units of output double, this is the exact number, 1 minus learning rate. So let's say I have produced 4 units, then they have doubled to 8. If I first, let's say I used 10 minutes, but now I've used 8 minutes, then you can determine your fraction by which the time has actually decreased, right? So you determine it by taking 1 minus learning rate. So what does this mean? This means that the lower the learning rate, now take this note. This one is very important. The lower the learning rate, the faster the learning and vice versa. So if in an exam you encounter something that maybe the learning rate has increased, know that by an increase in learning rate, this would obviously mean that labor would actually learn less quickly, right? So let's take a look at it with an example. Labor with a learning rate of 60% learn faster than that with a learning rate of 70%. All right. Why is this situation the case? Do you agree or not? This is because when units of output double, cumulative average time falls by this one. And to know that which learning rate is good, we take a look at the time fall by the fall of the cumulative average time. If cumulative average time falls much more quickly, it means that labor learns much more quickly. Why? Cumulative average time for the area, I mean for 60%, cumulative average time would fall by 40% because it is 1 minus 60%. While for the remaining, which is 70%, cumulative average time would fall by only 30%. You see this now, 70% seemed higher, but actually labor would fall, labor time, cumulative labor average time for labor would actually fall by a minimum amount. So that's the point you needed to grasp over here. All right, let's take a look at an illustration. Now, this is actually a graphical representation of cumulative average time, as you see here, against the cumulative units of output. So let's say for the first unit took 8 hours to complete, and then if the units were increasing, labor seem to learn more quickly, and so as you see, the cumulative average time was falling, but actually the time won't fall definitely, right? Because at a particular point in time, labor would be so accustomed to the job. If there are new processes, the processes actually labor would also be accustomed to the new processes, everything would be fine, right? So time would not get reduced anymore. That's why learning stops somewhere, and then we have this flat curve. All right. When learning stops, what do we mean? What is the learning rate when learning stops? What is the learning rate when learning stops? The learning rate is what is the learning rate? Because labor time no longer falls, so the learning rate is 100%. Learning rate is 100%. So when your learning rate is 100%, which we mean that labor has learned already for 100%, so no time can fall again. So I hope you get the real concept now about learning rate. Learning rate just shows you labor has learned by which amount, right? Okay. So learning stops at some point from which the incremental unit time for output remains unchanged. As you saw, after that time, labor would be consuming the same amount of time for each additional unit, and they call this a steady state point, right? Yeah. So we'll have a steady state point, and then everything would be fine. All right, let's take a look at the assumptions here. Now, for the learning curve theory to apply, we need to consider the following. You know, when working, you would have the worker, you would have the job itself, and then you would have the processes that are being undergone in order to produce the product. So you have to take a look at all those three segments, right? We have about 3 subjects. So first of all, the job should be repetitive. You know, if the job is repetitive, we mean that labor continuously learns, right? Yeah. Not that you do the job today, then you wait for a month or a week, then you do it again. We presume that work starts, learning restarts, right? To some extent, to some degree. But also about labor, we say that no labor turnover to enable continuous improvement. Of course, no labor turnover. If there is labor turnover, it means that when new labor comes, they'll have to start learning again, right? Okay, then no long breaks between jobs. Even if there is no labor turnover, we say that there should be no long breaks between the jobs. Because if there are long breaks, then labor just started learning, we say that labor will forget and they would have to start over again when they go back to the job. Also, we say that we should have a fairly difficult job. This too is obvious. You know, let's say that we have been given the job just to take the boxes from one corner of the building to the other corner. That actually doesn't need any learning. So that's why we say the job should be fairly difficult in such a way that labor needs learning to be much more efficient. Then we say that we should have manual jobs. Of course, if you are using machines, actually, it won't be appropriate to say that you are using learning rate, right? That's why learning rate is usually much more concerned with the labor. Although we'll see that in some other options that labor can actually make more appropriate use of materials, so materials can somehow be integrated therein. But our main focus here is labor. Okay, then we say there is a certain degree of motivation among employees. Of course, there should be some degree of motivation because if labor is not motivated, actually they won't even learn quickly, right, as expected. And lastly, we say production techniques should not change. Here I meant should not change, not may change. Production techniques should not change. Because if you change production techniques, even if labor have done the job maybe for a long time, they will have to relearn. So production techniques should not change. Let me rewrite this properly. Let me rewrite this. Production techniques should not change or do not change. So this should be the case, right? Okay, so that's all I wanted to speak of here. And now go to the learning curve equation. So let's be together until we reach at the final point.